Hello, everyone, and welcome to this presentation on the paper Driving Through the Concept Gridlock, Unraveling Explainability Bottlenecks in Automated Driving. This is a joint work between Infotech Labs Toyota and the University of California in San Diego. With this work, we really wanted to take a step towards explaining scenes of automated driving within the model through concept bottleneck models. Explainability models in general have helped user acceptance and understanding of autonomous vehicles. And concept models in particular typically explain their decisions by encoding information within a bottleneck layer of a model using a set of humanly defined concepts. In our work, we provide a method to use a concept bottleneck model within temporal automated driving scenarios, which goes beyond the typical use case of classification that has been shown in prior work. We use and provide a concept layer to explain sequential driving scenes. Rather than having it in separate components as previous explainability work has. So in the end, our goal is to explain changes in driving behavior and if they're being led by an external stimulus or a change in human preferences. The architecture of our model is dependent on images as well as sensor history. And the goal is to predict vehicle commands, in our case, steering wheel angles and distances. Similar setups, as shown on the screen, have been used by prior work. However, we use a text encoder that is part of the concept bottleneck that is then created through a similarity of images and text to help the model make their decisions in an interpretable way, as well as having the explainability part within the model. The longformer that we use helps with long temporal sequences that driving behaviors can have over multiple minutes. So we had to create a bottleneck, and we did this twofold. On the one hand, we used synthetic scenarios that we had generated by a large language model by prompting it to give us scenarios from traffic with respect to whether there were different traffic participants, driving behaviors, or surroundings. The language model would then give us different possibilities of what could happen. For example, a photo of a car changing lanes. We extend this bottleneck by human scene descriptions, which were available in the new scenes dataset, where they had very short description of what was happening in a scene. For example, there's a bicycle wreck, and we use these to get them into the same format that the model presumes. For example, a photo of a street with a bicycle wreck. The data that we use for our study contains both highway scenarios that have long sequences, for example, in the comma 2K19 data set, as well as shorter sequences in urban driving scenarios from the new scenes data set that have those natural language scene descriptions, but don't necessarily have long sequences. They're about 20 seconds. The results that we find with our model on those two data sets is that we can compete to black box models on the control command prediction, as we can see here on the evaluation of steering angle, mean average error, and forward distance, mean average error. We see that a concept bottleneck model plus a longformer can achieve competitive prediction. And the advantage of this approach is that it is inherently explainable with the concept bottleneck, and hence does not need as many features as well. However, we see that the bottleneck size does matter. We did an ablation between 25 to over 600 concepts, and we find a sweet spot at around 100 concepts. We find that the model has a difficulty to explain nuances. So if the concepts are too nuanced, it makes it harder to distinguish, as well as not having a clear separation or correlated or concepts that have something to do with each other can make a degrading performance. We also find that the concept curation method also matters. And we find that GPT curated concepts are actually more helpful than human created concepts for the same number of bottleneck nodes. To give an insight into the explanatory power, we had a look at what the model can actually explain and what its capabilities are within an automatic evaluation study of the common content words between the new scene's description and the actual prediction for the top 3 scenario. And we see that 81% of those top 3 scenarios were correctly predicted. We also did a human evaluation study where we see that between 90 and 94% accuracy on the top 3 predicted scenario has been shown in a human evaluation study by 3 evaluators, averaged over a majority vote. Keeping this performance in mind, we wanted to look at how we can use the model to explain different driving behaviors. And we wanted to do that by looking at the forward distance and how the model can explain why a longer distance would be kept compared to a shorter distance. And what we find is that for longer distances, those distances often occur in scenarios where there's nighttime driving, so there are street lights or artificial lighting illuminating the road. There could be a clear view of the road in daylight, meaning no traffic, meaning you can keep a larger distance, or difficult lighting conditions. So the driver just wants to keep space to the person in front of them. On the other hand, looking at small distances, we can see that the model correctly sees that there are lots of cars in close proximity, either on the front lane or the lanes to the left and right, meaning that it's correctly predicting that there's traffic, which would make sense why the distances are small. So we know that the model can explain what is happening inherently. For example, here are some more examples, and it correctly classifies that there are pedestrians or construction zones or passing a lot of traffic or driving at night. However, which parts of a long sequence of driving is actually important? This is where we looked at the transformer attention mechanism, which seems to be able to select important sections of a driving scenario and explain the changes. For example, we selected this one video to show where we see a significant spike in the attention as soon as we are passed by a trailer. And then as soon as the road is clear again, the attention drops again. So in summary, with this work, we provide a method to explain change in driving behavior with concept bottleneck models, which show competitive performance for automated driving scenarios with inherent explainability capabilities. We find that concept bottleneck size matters when training the model, and that the transformer attention can select important parts of the scene, as well as human created scenarios are not necessarily better than language model created scenarios. Thanks for listening, and if you'd like to see any more details, please have a look at the paper.